So let's take a look at my approach to these tasks. And don't worry if your code is different from mine. As long as it works, everything is fine. If you ask 100 programmers to write a piece of code to solve the same problem, what you will get is 105 different solutions. This actually shows that coding really is something super creative. And now let's take a look at my solution to the problem. So let's take a look at how this is done here. So the first what we do is we create a vector consisting of LiDAR points. We read the LiDAR points from a file. So that's a point cloud which I have stored in a special format here in the stat file, especially for this example. Then we create two size vectors using an OpenCV data structure. The first is called world size and the second is called image size. Now in world size, we encode the desired width and height of the sensor field which we want to create as a top view image in meters. So it's going to be 10 meters in width and 20 meters in length. The second is we want to create an image which is representing the world in pixels. And basically what it says is we want the 10 meters from the world size coordinate system to be mapped onto 1000 pixels in width. And the 20 meters in driving direction we want to map to 2000 pixels in height of the resulting image size. So that's the size of the actual top view image, which can also be seen here in the next line, where the CV.1 data structure is created. The variable is called top view image. It takes the image size, it takes 8-bit values in 3 channels, that's denoted by the C3 at the end here, and the image is going to be black by default. So 255 in all channels would be white, this is black. What we do then here, starting on line 571, we loop over all the LiDAR points we loaded from the file, and the respective iterator per iteration points to a single LiDAR point, which we then process here in the following. So the first which happens once we start iterating over the LiDAR point cloud is we retrieve the x coordinate, which is the coordinate in driving direction facing away from the sensor. A second is the y coordinate. It's the world position in meters with a y axis pointing left. What we do here is the actual conversion between the two coordinate systems. So xw and yw is in meters, in metric coordinates in the sensor coordinate system, and x and y here is in the actual image, in the top view coordinate system. So what you can see here, the transformation equations is they take the respective world coordinates, then they are scaled by the ratio of image size height versus world size height. So we look at the ratio between those two structures above here. So we divide image size 1000 by 10. So we exactly know what the mapping ratio between those two reference frames is going to be. And we add the height of the image size. And the same is done for x, and once you have completed this, basically what you get is you have a mapping between the pixels in the top view image and the respective position, the metric position in the sensor coordinate system. Now what we do here in this area, we first retrieve the z coordinate, z in world coordinates, which is basically the height above road surface. So 0.0 would be on the height of the actual LiDAR sensor, and the z-axis is facing upwards, so downwards we get negative coordinates, and the road surface is at about 1 meter 55, something like this, facing downwards from the sensor. So when we create a variable min z, as it is done here, and assign it the value minus 1.4 meters, what we do is we basically tell the system to not consider any points which are below this minimum z threshold. So all the points which are above the threshold, which are above the road surface, are considered for display. The rest is simply ignored. And what's done here in this area here, so all the points which are sufficiently high above the road surface, and also you might want to play around with this value here to see what the resulting top view image looks like when you, for example, adjust it to 1 meter 60 or 1 meter 30 or even 1 meter. Just take a look at what the respective image looks like. It's quite interesting because when you change this value and for example imagine a car with a certain width, and you have basically a point cloud representing this car, and it narrows down while you get to the roof, because the widest perimeter of the car is approximately on the height of the tail lights. And if you adjust the scan width or the height, the min z variable, to a setting, for example, let's say minus 0.8 centimeters, what you will see in the resulting top view image is that the car which you scan actually gets narrower because you move upwards in the respective z threshold. Okay, so in this area here, what you do is you assign a color value to every LiDAR point. So the first thing we do is we retrieve the X value in driving direction. That's our scaling value. What we want to do is we want to color code the distance from the sensor so that close points appear in red and far away points appear in green. And that's why when we jump down to this line here where we draw the actual circle into the top view image, we provide it with the coordinates in the pixel framework. We say, okay, one LiDAR point should have a radius of 5 pixels, and then that's why I've jumped to this line here. Then we assign it a color value which consists of a 0 in the first channel, and which is the blue channel, and then we have the green channel here and the red channel here, and those values, they are controlled by the ratio between the respective X value of the LiDAR point versus a maximum value here. And the maximum value which we get here is world size point height. And the world size point height variable has been set up here. It's 20 meters. That's the maximum distance which the top view image allows for in terms of displaying LiDAR points far away. So 20 meters is going to be bright green and 0 meters is going to be bright red. And that's the scaling value which we use here. So maxval denotes 20 meters. Now the red channel should be 255 when we have a distance of 0 meters away from the sensor. And actually that computation is done here. So we take the actual X value, subtract from it the maximum value, and then scale it by the maximum value. Now let's make a short example. Let's assume we have a point directly in front of the sensor, which is going to be 0 meters. So we have 0 minus maxval. We then compute the absolute value, so the sign gets lost. So basically what we have here is we divide maximum value by maximum value, which is 1, which leads to this product here to be 255, which assigns 255 to the red channel. The same is done for the green channel, with the only difference that we do not take the absolute value of this difference here, but instead we take the absolute value of the difference, but subtract it from 1. So we invert the green channel to be exactly the opposite of the red channel. So let's make the same example here. So value 0 meters directly in front of the sensor. We subtract from it max value, which is 20 meters. That gives us a 1 here. And now we have 1 minus 1, which is 0. So at position 0 meters away from the sensor, the green channel is at 0. And if we move away to, let's say, 20 meters, we have 20 meters minus 20 meters, which is 0. So we have 1 minus 0, which is 1. So at 20 meters distance, the green channel is going to be 255. And the red channel, if you run the same numbers here, is going to be 0. So the circle which is being displayed is color-coded in terms of the distance away from the sensor. And we do this by shifting the color bands and scaling them with regard to the actual distance of the sensor point away from the sensor. So that's happening in this loop for all LiDAR points. The next thing which happens here is we plot the distance markers onto the top view area. It makes sense to have a rough feel for how far away certain objects are. And also when you look at the image sequences which we are using in this course, you will see that it's helpful to have a feel for how far away objects in the top view image are. And in order to make this easier, we simply plot distance markers with a line spacing of 2 meters. So what we want to achieve is we want to have a horizontal line every 2 meters on the entire top view image so that we can easily see where objects are. So we can do this by running over this loop here, which basically says we compute the number of markers scaled in terms of the current height of the top view image. So top view image currently is 20 meters in height. We divide this by the line spacing, which is 2 meters, which gives us 10 markers, which we put into the image. And we now loop over those 10 markers here. And every 2 meters, we simply paint a blue line which runs horizontally across the top view image. And then the last thing which remains to be done is to simply display the actual top view image. Let's run this code to see how it looks. And what you can see here is a very nice rendering of the scene in front of us. So close points are color-coded bright red, and while we move away from the sensor into driving direction, that's the 20-meter mark. We can see that the LiDAR points at the far end of this 20-meter mark are painted bright green, just as we wanted it to be. And in the middle, we have a certain mixture, a gradual transition between red and green. Now the line markers, this is the 2 meter mark, 4 meter mark, 6 meter mark, 8 meter mark, and the vehicle directly in front of the sensor, this one here, is at a little less than 8 meters away. And we will be using this vehicle here very, very thoroughly in terms of computing time to collision in a later section of this course. And you should recall that this is roughly 8 meters away from the sensor, and when this vehicle brakes, this edge here is moving closer to the sensor, which enables us to compute an estimate of the time to collision. So that's the code for rendering a top view image. So as you just saw, generating a top view image is pretty easy. The only thing where you have to think a little is the conversion between world coordinates on one side and top view coordinates on the other side, but that's about it. And now we are able to visualize LiDAR data and also use color to show an additional layer of information. And if you feel like it, why not replace the distance coloring, which we use now, with a reflectivity coloring to see which objects reflect the laser well and which don't. But now let's move on to the next section where we want to start working on a way to project LiDAR points onto the image plane so we can visualize them directly in the camera image.